All right, let's take a look at the following example. We're going to use the ICE table along with the quadratic formula to solve for the relative change x. And once we find the relative change x, we can find the actual change, put that change back into the ICE table, and solve for our concentrations at equilibrium. So what we want to do is we want to begin with an overview of the information that the problem gives us. We have a concentration of N2O4 that contains 0.0250 molar. So if we look at this equation, we can write out our ICE table, our reactants N2O4, and our product. We only need one column here because we only have one product. So initial change and equilibrium. So in the problem, we're given that the reaction mixture only contains 0.0250 molar of N2O4, and there is no reactant initially. So what we can do at that point, we can make a QC comparison where QC is equal to the concentration of NO2 squared over the concentration of N2O4. So QC then would be equal to 0 squared over 0.0250, and that is equal to 0. So in the QC to KC comparison, we can say that QC is less than KC, this value here, and reaction proceeds to products. Now we have to make that assertion between KC and QC because we need to know which direction the reaction will proceed, and if the direction of the reaction is going to proceed to the right, that means our change is going to be a loss in concentration of X and a gain in concentration of NO, which is the product. So our stoichiometric coefficient for N2O4 is 1. Our stoichiometric coefficient for NO2 is 2. So when QC is less than KC, we know we're going to lose reactants and we're going to gain in products. So at equilibrium, when I add these two columns together, I have a 0.0250 plus a negative x. That would be 0.0250 minus x. When I add these two columns together, I would have 0 plus 2 times x, which would be 2x. So when I write out Kc for this reaction, I need to take this row that has the equilibrium concentration expressions, which would be the concentration of NO squared divided by the concentration of N2O4, and that's going to equal to, I need to take the NO concentration here, and I need to put in 2x, that needs to be squared. I need to take the N2O4 concentration here and put that in, and that's going to be 0.0250 minus x. So at that point, I can then set this equal to my equilibrium constant here of 0.36. So this is the equation I will use to solve for the change in x. So if I rewrite this out step by step, I would have 2x squared divided by 0.0250 minus x, and that's equal to 0.36. So what I can then do is I can cross multiply or set up an expression that says 0.36 times 0.0250 minus x. Set that equal to 2x squared. So what I did was I cross multiplied here and cross multiplied there, and that gave me that expression. Now what I want to do now is I want to multiply 0.36 times 0.025, and that's going to give me 0.009. And then I want to distribute, and multiply 0.36 times a negative x. That's going to be minus 0.36x. And I want to set that equal to 2x squared, which is going to be 2 squared, which is 4, and x squared, which is x squared. Now, at this point, I want to rewrite this equation in the form of ax squared plus bx plus c equals 0. That is called standard form. So I want all my terms, including my linear and my constant, all on one side. That is going to allow me to solve for x. So if I rewrite this and put this in standard form, that's going to be 4x squared. If I bring minus 0.36x over, that's going to be plus 0.36x. And if I bring 0.009 over to that side, that's going to be minus 0.009. And I'm going to set that equal to 0. So at that point, I can now use the quadratic formula that says the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. So this is my a term, which is equal to 4. This linear term, x, that's b, is equal to 0.36. This constant, c, is equal to negative 0.009. So that's what I need to plug in here. So I'm going to have two expressions, actually. So that's going to be the opposite of b, which is 0.36 plus or minus the square root of b squared, which is 0.36 squared minus 4 times a, which is 4 times c, which is negative 0.009. All of this divided by 2 times a, and a is 4. So what that is going to simplify to is I'm going to have negative 0.36 plus or minus. When I do the operation under the radical and take the square root of it, I'm going to get this number of 0.523, and that's both all divided by 8. So I wind up with two solutions. That's going to be a negative 0.36 plus 0.523 divided by 8, and negative 0.36 minus 0.523, all divided by 8. Now, if we look here, we can see that this negative minus another number is going to give me a negative number when I solve for x. And I should have put x is equal to out here. So when I solve for x, this is going to give me a negative number. If I put that negative in for 2x, that's going to give me a negative concentration. So we can exclude that value. And what we would wind up with from this value, when we took a negative 0.36 plus 0.523 and divide by 8, we get 0.0204. Or you could say 0.523 minus 0.36. However you think about it, that's going to give us a 0.0204. That is the root or your solution to x for this quadratic equation. When I put x in to this quadratic equation, it will give me a solution of 0. That is your solution, that is your root, that is your x-intercept, whatever you called it in algebra. So now what we have to do is we have to go up to the ICE table and put in our value for x that we solved for. So that would be 0.0250 minus 0.0204. 0.0204, and then we will have 2 times this x value of 0.0204. So for N2O4, x is 0.0046, and for NO, it should be 2. For NO2, x is 0.0408. So those are my, right here, when I put my change back into the ICE table at equilibrium, these are my equilibrium concentrations. So if I erase some of this math, we can plug these numbers back in. Remember, this is x. This is the x that we found. So when we plug those back in, these are our equilibrium concentrations. Okay, so now we can plug this expression back in and see if we do get 0.36. Let's just go ahead and put 0.0046. Wait, the wrong one. I need this guy right here. That would be 0.0408. That would be squared. And divide that by 0.0046. And is that approximately, question mark, equal to 0.36? Is that approximately equal to that value? So what we do is we take our calculator and we plug that number in, and I get that this is equal to 0.361. So yes, that is approximately equal to 0.36, our KC value. So at equilibrium, what we have found is the concentration of N2O4 is equal to 0.0046. And at equilibrium, the concentration of NO, that's 2 there, concentration of NO2 is equal to 0.0408.